Hello, everybody. We're back for continued coverage of higher order functions in Chapter 14. We're still in Section 14.3, but now we're looking no longer at map and its relatives, but walk and its variations. Walk is rather similar to map, but we use it partly because it's nice for producing side effects, but also because unlike map, which takes a .x argument and applies a .f function to each element of it, walk does the same thing, but whereas map constructs the results of the .f function and sticks them together somehow, walk will just return whatever .x it was given. So you can use it to pipe into some other function construction that might be needing to accomplish some other stuff with that .x iterable. Sometimes wonder why walk got its name, and maybe it's from the idea of responsible hiking. When you go into a wilderness area, they say pack it in, pack it out. And so walk, it takes the .x in, but it gives the .x out. It doesn't leave it anywhere. Anyway, let's practice a simple thing with walk. Here we're just going to use it for side effects. We're not using that special great property it has of returning the .x. We're going to rewrite a familiar function that you learned back in Chapter 4 when you were working on flow control for the first time. You may remember writing a function called pattern that had two parameters, car and in, and the idea was to produce pattern structures like this function called down here, where car is quotes A and in is 7. I'm going to go ahead and teach pattern in the global environment, run that function, and you start with 1A, then 2, then 3, then 4, then 5, then 6, then 7, and then you start stepping down 6, 5, 4, 3, 2, 1. So you may remember a for loop that you set up for that. So unsurprisingly, you can use a higher order function to do the same thing. Let's use walk. Inside of pattern, you set up a vector that's going to be the line lengths for all your lines. So it's got to be done by concatenating together the numbers from 1 to n, and then the numbers from n minus 1 to 1. That's going to be the .x argument for your higher order function. You also need a .f argument. You need a function that takes care of one line at a time. So I call it the line here. It's a function of whatever character you're going to be making it out of and how many times you want to repeat that character, which I'll also call in. And all it does is cat the rep of car times is in. Sticks on a new line, so you'll go down to the next line. Sep is the empty space. And so then, here's the key thing. Line length gets piped in as the first argument, the .x argument to walk. The .f argument is the line. And you also need another argument to the line. And so you say car is car. This is the car that is provided up by the user here when the user calls the function. And so because you've said that here in the walk call, then walk figures out that line length must be the in parameter in the line. And then the car is going to be the car parameter. And so that's how it produces the same effect as a for loop. And so this is what you do here is you walk the line, kind of like Johnny Cash in the song. So there's just some weak computer science humor here. I considered inserting the video of the song, but that would be too silly. So now for a little bit more of a real example. In this example, we're going to utilize the return value of walk. So what we'd like to do is a twofold task. We want to start with all the numerical variables from the data frame M111 survey. And one, we want to save plots of each one of those numerical variables, density plots of each of those numerical variables. But we also want to print out summaries of them to the console in a nice, organized way, numerical summaries to the console in an organized way. So our basic idea is we'll use pwalk to do the plot saving, but because pwalk returns its argument, we can use the same information to go and make another higher order function piece together the nice numerical summaries. So before we do anything, we need to create a directory that holds the plots. I've set the working directory to be the source file for this our markdown document. I'm going to go ahead and make sure that I'm doing that. Am I saving it in the right place? Yes, indeed. All righty. So you'll notice in this CSC 215 directory here in my local RStudio, there is no directory called plots. So when I look at this if statement, it's going to be true that plots does not exist. So we're going to do a dir.create, create a plots. Let's see if that happens. Yep, there it is now, down here. And next, we get the numerical variables in M111 survey. So I'm going to run this little code chunk for you, then we'll take a look at how does its work. Oh, wait, before I do that, let me clear out the global environment from the previous example, just make it easier to see. All right, so let's run this code chunk. And notice that numericals is 71 observations of 6 variables is another data frame. It started with M11 survey and piped it in as the first argument to this function called keep. Now that's from the purrr package. The way keep works is it has 2 arguments, a .x and a .p. The .x is some vector or list or other iterable thing. The .p is a function, but it's a function that returns either true or false. And what you do is you just keep the stuff in the .x where the function returns true. And keep tries to return the same sort of thing as the .x that it was given. It was given a data frame, and so it returns the numerical variables in a data frame. Now, we're also going to need the names of the numerical variables. So I'm just going to take the numericals and pipe them in as the argument to the names function, and here's that little character vector of the 6 names. So notice, check it out here, numericals. It really is just the numerical variables from the original M111 survey. Here are their names as num names. Okay, let's get more to the task here. If we're going to save graphs for all of the numerical variables, then we need a function that saves the graph for one numerical variable at a time. So that's our saveGraph function here. It's going to need 2 parameters. The actual vector of numerical variables shall be called var here. And var name is a string that's the name of that numerical variable, and it'll be used to create a title for the plot. So in the body of the function, you use ggplot. You do not need to work with a data frame because all you're going to work with is var. You aesthetically map the x position to var, and then you tack on a geom density. And then you also tack on a title where you paste together density plot for whatever the var name is. So you bind the name p to the results of that. So you're not actually making a graph right now. You're just saving it into p. And then there is a ggsave function where you can save a plot object into a file. You have to say what the file name is. And so you stick together plots/density_ the var name .png at the end. The reason is that you're with the device parameter, you're setting the type of plot you're making to be a PNG, and you have to specify what is the object that you're going to make that file out of, and it's the P. Okay, so we need to teach that to the global environment. We're also going to need a function to produce a summary of a single numerical variable. So that's called make summary here. It's a function of two things. X shall be the vector of numerical values, and var name is a string that's the name of the variable. 5num. Hey, let's remind ourselves what 5num is if we don't know already. 5num, it just takes a numerical vector. How about a 1 through 10 down here? And let's run it. What it does is it produces the minimum, 1, the first quartile, which turns out to be 3, the median of the numbers turns out to be 5.5, the third quartile, and the max. So, those are the numbers that are used in your standard box plot. So anyway, the name 5 has been bound to a vector like that. And then you just create a little list of 6 items. Each item has a name. Variable is the name for the string that is the name of the variable. Min is the name for the minimum of the numbers. And similarly for Q1, median, Q3, and max. So let's teach make summary. And let me go ahead and run it down here on an example. How about make summary on the numbers 1 through 10 just to see if it works. Oh, shoot. That's right. I need to provide the var name. How about, example. And there we go. It's that named list of 6 items. Okay. So we've got our one at a time function. And we saved it to the global environment. Very well. We're now ready to actually walk through the process. We'll actually use the function pwalk, which relates to walk, just like pmap relates to map. It has a .x parameter and .f parameter. The .x parameter is a list of the iterators that will get to vary, and the .f is the function that works on the successive elements of the list. So in our particular application, the .x is going to be a list with 2 elements, the data frame of numerical variables and the vector of names of these variables, and the .f is going to be the save graph function. So what's going to happen is the save graph function is going to be made to work on, first of all, the first variable in the data frame and the first name. Then it works on the second variable in the data frame and the second name, making and saving the graph in that way. For the second part of our Odyssey, after we do the first walk, we'll get that same list back of the data frame and the names. And we're going to take that list and we're going to construct a data frame that makes up the summary of all the variables, but we're going to construct it row by row. And that's done with a purrr function called make dfr. So let me just show you how it works here. So you make a list out of numericals and num names. Remember, numericals was the data frame, num names is the names. You send that in as the .x to pwalk, and here's the .f as save graph. So that's going to do the saving of the graphs into the plots directory. But out of it comes that same list. And it gets piped into pmap dfr as the .x element. The make summary function is the .f, and it's going to work on the first numerical variable and its name to produce a summary as a list. Then the second numerical variable and its name makes a list for its summary. And it's got, at the end, it's going to have 6 lists, but it's going to stick them together to be the rows of a new data frame. So let's give it a try. So it thinks for a while, and let's see if it did its work. Let's look inside of plots. And lo and behold, plots is populated with little graphs, well, with little files that have the titles that look like what makegraph was supposed to be doing. Density underscore diff.ideal.act. Hey, that was one of the names in Math 1 of the survey. It was numerical. Density underscore fastest.png really looks like the real thing. Let me just open up one of these and see if it, oh, look at that. Sure enough, there's a density plot of the fastest speeds ever driven. So that part worked. But look also what comes out into the console, a data frame, where there are 6 columns. There were 6 items, remember, in the list that's produced by Make Summary. Each row in this data frame started out as one of those lists, but it's been stuck in as a row in this new data frame. So that's pretty cool. All that stuff out of a very simple walk followed by a pmap. So make sure you work through this on your own and hit those practice exercises hard to deepen your understanding of higher order functions in the purrr package. See you later.